In the previous video we looked at definitions for distance, displacement, speed and velocity. We're now going to link them up a little bit in a more graphical way. As you can see here, we've got a graph. We'll be looking at a distance versus time graph to begin with. Before we get into those ideas, I want to just draw your attention to some of the things that you should be including when you label the axes for a graph. Usually there's going to be three things you need to include. First is the quantity itself, so the name of the quantity. The second thing is then the symbol that you would use to represent it, and then the third thing is the units of measurement for that that particular quantity. So in that axis it'll be distance, the symbol there is S, and the units are meters, and on the horizontal axis it'll be time. The symbol there is T, and the units of measurement will be seconds in this particular case. Now what we're going to have a look at here is a particular example, and just a bit of a trivial thing, but imagine, if you will, say a dog that's running in a dog park, and you're measuring the distance as it's moving along. Obviously it'd start timing from t equals 0, so we'd have a point down here, and then let's say at 20 seconds later you've measured the distance that the dog has travelled to be 10 metres, so we're up in that top right hand corner. If we were to then join those 2 points together, so we have a line representing the motion of the dog, we can see there that for each second we could plot what the position of the new distance of the dog would be, and so we've got a representation of the dog's motion. Now the useful thing about that is that we can now tie that into speed as well. If we think about the definition for speed, we said that speed was the rate of change of displacement, rate of change of distance, rate of change of distance with respect to time, or of distance over time. That corresponds graphically to the gradient of a distance versus time graph. So the gradient of a different distance versus time graph is speed. So if we were to write that mathematically, we'd say that the speed v is equal to the change in the vertical axis, or the rise over the run, which would be the change in the horizontal axis, in this case the time. So we'd have our speed equation could be represented as the change in distance over the change in time. Now if we go back to this particular example, the total distance covered here is 10 meters. So if you look vertically, it's covered a distance of 10 meters, and it took a time of 20 seconds to do that. So we could then say that the change in the distance is 10 meters, and the time over which that occurred was 20 seconds, and so in this particular example we'd say that the speed of the dog was 0.5 meters per second. So fairly easy calculation. Now you may recall in the previous video I mentioned a couple of different ways that we might refer to speed, and I'll just elaborate on those now. So the first one is average speed. Average speed, as the name suggests, is an average measure. So average speed is basically just looking at how far it's travelled, how long it took, and calculating the speed as a result. So average speed is calculated using the total distance travelled divided by total distance travelled over the time taken. Now, in a sense, the path that's taken here, it sort of doesn't really affect the calculation or what happens along the journey itself. It's simply the total distance over the total time. That calculation is the example above. So we've got the distance travelled and the time taken, and we've figured out an average velocity. Now, realistically, motion's not always going to be as simple as just a straight line from the origin to the finishing point. Instead, we're going to often have a bit of a different path that in this case the dog, he may have instead of just sort of moving in a straight line at a constant speed, might have been that he for 2 seconds he ran out to 4 meters and then started sniffing at something on the ground perhaps, and was doing that for 10 seconds and then started to run again and ended up getting to that 10 meter distance after 20 seconds. So you can see there in that particular graph there's a different path, I suppose, or not path so much as the time over which the distance has been covered, and as a result the speed of the dog, the average speed of the dog would still be the same, but you can see throughout that motion that the speed at various points in time have varied. So that's why we need to look at the next quantity after average speed being instantaneous speed. Now instantaneous, if you look at the first part of that word, or the root of that word, instant, basically just means that we are looking at the speed taken at a particular point in time, or a particular instant in time. It's still going to be calculated using the gradient. So if, for example, we looked at that graph above, and we wanted to say, look at the time of t is equal to 18 seconds. So I'll just go back and look at the graph up here. So at 18 seconds, we're dealing with this point here. That means that we need to find the gradient of this section. So finding the gradient of that section will give us the instantaneous speed at the point of 18 seconds. Now we could use any 2 points along that line. We've got a whole line there, so it's better to use the points that are furthest away from each other. So we'll use the extremities of that line segment. So this point here is 14 seconds and a distance of 4 meters, and this point here, as we saw before, was 20 seconds and a distance of 10 meters. So we can figure out the speed, instantaneous speed at this point here, by doing the calculation of the speed being equal to the change in displacement, keep using the wrong word, change in distance over the change in time at that particular point. And as we said, the distance, or the extremities of that line segment, were 10 meters minus 4 meters, and the time was 20 seconds minus 14 seconds. So that will give us a value of 6/6, and will give us then a speed of 1 meter per second. So for that particular point in time, t equals 18 seconds, the instantaneous speed is 1 meter per second. Now that, because we've got a line segment here, basically anywhere along that line segment it has the same gradient, so we know that anywhere from 14 seconds to 20 seconds the dog was moving at 1 meter per second. Now if we look at the time from 2 seconds to 14 seconds, we can see there that the distance hasn't changed, and so its speed would be 0 meters per second. In other words, the dog's stationary, not moving anyway. And in the first section there, moved 4 meters in 2 seconds, so 4 divided by 2 would give 2 meters per second. One last point about these graphs, because distance is a scalar, the gradient will always be positive. Now that's going to become more important when we go into the next graph, but I just want to make that point here. So the gradient of a distance versus time graph will always be positive. So something to keep in mind for these types of graphs.